We have looked through homework 1. Actually, a large amount of homework afterward. Look like the same as this one. You will have a bunch of training data. And in these training data, there will be pairs of X and Y. There will be X1 and its corresponding Y1 head. There will be X2 and its corresponding Y2 head. There will be Xn and its corresponding Yn head. Testing data. The testing data are that you only have X but no Y. Everyone has looked through homework 1. In fact, all the homework afterward looks very similar in format. For example, homework 2 is to do speech recognition. Our X is small part of voiced speech signals. Actually, it is not the real and complete version of the speech recognition system. It is a simple version of the speech recognition system. X is a small signal. Y head is to predict which phoneme corresponds to this small voice signal. It doesn't matter if you don't know what phoneme is. Just think of it as a pronouncing dictionary of American English. Homework 3 is called image recognition. Our X is a picture. And Y head is what kind of things in this picture. That predicted by the machine. Homework 4 is speaker identification. What is the purpose of speaker identification? What the speaker identification to do is that X is a sound signal. But Y head is not a phoneme now. Y head is the person who is talking now. You can imagine such a system is very useful now. If you call the customer service of the bank, there is now an automatic speaker recognition system. It will check that people who call in now is the customer or not. It spends less time for the customer service staff to do identity verification. Homework 5 is to do machine translation. It is doing machine translation. X is a certain language. For example, this is the only Japanese sentence I know. Itamido shide. Its Y head is another sentence like this. Okay, now you can flood the message board with something like Ju Ko Chun Fu. What are the training data used for? Training data will be used to train our model. The process of training a model has been talked about last week. The training process has 3 steps. First, you have to write a function with unknown parameters. These unknown parameters will be denoted as theta. All unknown functions in a model. So f theta of x means I now have a function called f of x. There are some unknown parameters in it. These unknown parameters are denoted as theta. Its input is called x. This input is called feature. Then, you have to set something called loss. Loss is a function. The input of this loss is a set of parameters, and the loss function is to judge whether this set of parameters is good or not. Next, you have to solve an optimization problem. You are going to find a theta. This theta can make the value of loss as low as possible. The theta that can make the value of loss the lowest are called theta star. With theta star, you can use it on the testing data. That is, you bring theta star into these unknown parameters. Originally, there are some unknown parameters in f theta of x. Now, this theta is replaced by theta star. It is replaced by theta star. Its input is your current testing data. You need to save the output result and upload it to Kaggle. It's over. Next, you will face a problem that directly executing the sample code provided by the TA can only give you the result that over a simple baseline. If you want to do better, what should you do? Here is a guideline of how to make you do better. It works for all early stage homework. This is just like the character of Guan Yu. You can get it at the start. It can help you beat all the early stage enemies of the game. What is the guideline? Starting from the top. The first one is that if you think you are not satisfied with the results on Kaggle, what is the first thing you have to do? Check the loss of your training data. Some people may say that you should only care about the loss of testing data, because the result on Kaggle is the result of the testing data. But, you have to check your training data first. Look at your model on the training data. Did the model learn anything? After that, go to see the results of the testing data. So, what you have to check first? is the loss of the training data. If you find that the loss of your training data is high, it did not learn well on the training data. Next, you have to analyze the reason for not learning well on the training data. There are two possible reasons here. The first one may be the bias of the model. The bias of the model is told about in last week. The so-called model bias means that supposing your model is too simple. For example, we now have a function with unknown parameters, and these unknown parameters could be replaced by any kinds of numbers. You get a function with theta 1, and this function is represented by a point, and you get another function with theta 2. You could combine all these functions to get one function set. But this function set is too small. In this function set, there is no function can reduce the loss. Functions that can make the loss lower don't belong to the range that your model can describe. There are unknown parameters in your model. The unknown parameters could be replaced by any values. With these values, you get a function set. With different values, you could get different functions. Combining all the functions, you get a function set. In this set, there is no function which can reduce your loss. In this situation, even if you could find a theta star, which is, in these blue functions, the best one, which is, in these blue functions, the one that can make the loss lowest, but to no avail. It is just the king among all losers, which is still a loser. The loss is still not low enough. This situation is just like that you are trying to find a needle in a haystack. Here, the needle refers to a function with low loss. However, the needle is not in the haystack at all. In vain. You can't find the needle no matter how hard you try. Because the needle is not in your function at all. Not in your haystack at all. So, what should we do? We should redesign a model at this moment. But, how should we do? To give the model more flexibility? We demonstrated last week. For example, we can increase the input features. We said last week. Originally, the input features are only from the information one day ago. Supposing that we want to predict the number of viewers with the information one day ago, it is not enough. How about we use the information from the last 56 days? The model becomes more flexible. You can also apply deep learning to improve the flexibility. So, if you feel that your model is not flexible enough, you could add more features. You could design larger model, or you could apply deep learning to increase the flexibility of the model. This is the first possible solution. But, you should notice that, while training, high loss doesn't mean model bias in all cases. You may encounter another issue. What is this issue? The issue is that the optimization is not so good. What does it mean? We know that the optimization we use in this class is gradient descent only. In this kind of optimization, there are many issues. For example, we mentioned last week that you might get stuck in the local minima. You can't find parameters that can actually make the loss very low. It could be visualized like this. This is your model. It could describe the set of functions. You can replace theta by different values to form different functions. Putting all the functions together, we could get this blue set. Inside this blue set, it does contain some functions. These functions have low losses. But, the problem is that, for the gradient descent algorithm, it can't help us find out the function with low loss. Gradient descent says you want me to solve the optimization problem, and it give you this theta star, then that's all. But, this theta star does not give me the loss low enough. In this model, there is a certain function with loss low enough. Unfortunately, gradient descent didn't give us this function. It's like that we want to find a needle in a haystack. And we actually know the needle is in the haystack. But we cannot pick the needle up. Here comes the problem. We see that when the loss on training data is not low enough, is it an issue of model bias? Or is it an issue of optimization? Today we find out that when we can't find a function with low loss, Is it because the capacity of our model is not high enough? There are no needles in the ocean. Or, the capacity of our model is actually enough. It's just because the gradient descent is not strong enough to get the needle out. Which one is it? Is our model gigantic enough? Or is it actually not big enough? How to judge this? Here is a suggested method of judgment. You can compare different models to know that whether the model is big enough or not. How to say? Let's take an example here. This experiment is from the paper of the residual network. We put the paper link in the upper right corner. There is a story at the beginning of this paper. It says that I want to train two networks, one of which has 20 layers, and the other has 56 layers. We test them on the test data. This horizontal axis refers to the training process. It shows how your parameters update. With the parameter update, the loss of your model will get lower and lower for sure. Here, note that the loss of the model with 20 layers is relatively low, and the loss on the one with 56 layers is relatively high. This residual network is a relatively early paper, which is proposed in 2015. If you are a university student now, you were still a high school student then. So at that time, most people didn't know much about deep learning then. For deep learning, there are many kinds of weird misunderstandings. At that time, the phenomenon in this figure is regarded as overfitting. For most people, they may tell you that deep learning doesn't work. The model with 56 layers is too deep to work. Models don't need to be so deep at all. At that time, not everyone thought deep learning is good. The effectiveness of deep learning is still questionable. With the experiment mentioned above, someone will say that those deeper models are actually bad. This is called overfitting. But is this overfitting? This is not overfitting. I will tell you what overfitting is later. Not all bad results are called overfitting. You have to check the experiment results of the training data. After you check the training data of both models, you will find that the training loss of the network with 20 layers is lower than the training loss of the network with 56 layers on the training data. What does this mean? It means that the optimization of the network with 56 layers is not done. The optimization is not powerful enough. You may ask, how do I know make sure that it's the optimization issue? Maybe it's model bias. Maybe it's because the capacity of this 56-layer network is not good enough. It may need 156 layers. And 56 layers are not enough at all. But after you compare the 56-layer network to the 20-layer one, the loss of the 20-layer network can be so low. The capacity of a 56-layer network must be greater than that of 20 layers, isn't it? A 56-layer network can easily do what a 20-layer network can do. It only needs to make sure that the parameters of the first 20 layers are the as that 20-layer network, and do nothing for the remaining 36 layers. They merely copy the previous layer's outputs as their outputs. As a result, a 56-layer network must be able to do what a 20-layer network can do. Here, the 20-layer network can already reach such a low loss, and the 56-layer network has higher capacity than the 20-layer network. So it doesn't make sense that the 56-layer network can't do what a 20-layer network has done. So for the 56-layer network, if your optimization is successful, the loss of it should be lower than the loss of a 20-layer network. But for the training data here, the result doesn't match obviously. This is not overfitting. And this is not model bias, either. Because the capacity of a 56-layer network is enough. The problem is because your optimization is not strong. The optimization is not good enough. So the previous example can tell us. How do you know whether your optimization is good or not? The suggestion for you here is, for those problem you have never seen before, maybe you can use some smaller or shallower networks first. Or, you can even use some traditional method rather than deep learning. For example, linear model. For example, support vector machine. There are some methods such as support vector machine It doesn't matter if you don't know what it is. The optimization may be easier for you. The optimization of them seldom fails. These models will do their best to find the best parameters. They are less likely to fail. So you can train some relatively shallow models, or some simpler models first, to have an idea about the kind of loss you can get from these simple models. Then you can train a deeper model. If you compare the two models, and find out that even though the deep model is more flexible, it still can't have a loss lower than the shallow model, that means there is a problem with your optimization. Your gradient descent did not work well. You will have to find some other methods to do better optimization. For example, we saw this last time when we were predicting the number of viewers we set on the training data, which are data from 2017 to 2020. A network with one layer has a loss of 0.28k. It decreases to 0.18k with 2 layers, 0.14k with 3 layers, and 0.10k with 4 layers. However, when I trained with 5 layers, the result becomes 0.34k. How did this happen? We have a bigger loss now. How did this happen? Is it due to model bias? Clearly not. Because we achieve 0.10k with 4 layers. And we should be able to lower it with 5 layers. There's a problem with optimization. Something's not done well when we're doing optimization. Which caused the problem? Okay, if we didn't do optimization well, what should we do? In our next session, I will tell everyone what to do. Now, you just have to know this problem exists. You need to know how to distinguish between model bias and optimization. If your training loss is high, if it's due to model bias, then make the model bigger. If it's because the optimization fails, then we'll see how to solve this problem in the next session. Okay, now suppose you have gone through some hard work. You can already make your loss on training data lower. Then you can check the loss on testing data. Check how the loss on testing data is. If the loss on testing data is also low, if it is lower than the strong baseline, it's over. There is nothing left to do, okay? But if you think it's not low enough, if the loss on the training data is low, but is high on testing data, then you might actually have a problem with overfitting. Pay attention here, only when having low training loss and high testing loss can it be called overfitting. Many students, upon seeing bad results on the testing set, simply say it is overfitting. It is not necessarily overfitting. If you have a result and ask me, "Professor, how can I have a better result?" the first question I will ask you is, your loss on the training data. What is your loss on the training data? I found that 8 out of 10 students will say, the loss on training data? I did not record training data's loss. You have to record training data's loss. Make sure that your optimization is okay first. That your model is big enough. Then, check if there's a problem in testing. Okay, if the training loss is low, and the testing loss is high, it could be overfitting. Why does overfitting happen? Why is it possible that the training loss is low, while the testing loss is high? Here is an extreme example to tell you why this happened. This is our training data. Assuming that based on these training data, a certain crappy machine learning method found a function that was less than useless. This useless function, what does it look like? This useless function says, if today the input is x, then we'll find if this x is present in the training data. If x is present in the training data, then we take its corresponding y hat as output. If x is not present in the training data, what to do then? It just outputs a random value. You can imagine that this function did nothing. It is less than useless. But even though it is a useless function, its loss on the training data is 0. When you input all the training data into this function, its outputs are exactly the same as your training data's labels. So on the training data, this useless function has a loss of 0. But on the testing data, its loss will become very large. Because it doesn't actually learn anything. This is a more extreme example. However, under normal conditions, something similar might happen. For example, suppose the input feature is called X. The output label is called Y. Both X and Y are one-dimensional. The relationship between X and Y is this quadratic curve. We deliberately use a dotted line to represent this curve, because we usually have no way to observe this curve directly. What we can really observe is our training data. You can imagine the training data as random samples from a few points on this curve. If the model is very capable, if it has great flexibility, if it's very flexible, you only give it 3 points. It will know that we need to make the loss low at these 3 points. So the curve of your model will pass through these 3 points. But other places without training data as a limitation will be freestyle. Because of its great flexibility, it's very flexible. So your model can turn into a variety of functions. You don't give it information for training. It will have freestyle, producing all kinds of strange results. At this time, if you input your test data and training data are not exactly the same, of course. They may be sampled from the same distribution. The testing data are the orange dots. The training data is these blue points. After using these blue dots and find a function, you test it on these orange dots. Not necessarily good. If your model has a lot of degrees of freedom, it can produce very strange curves, leading to good results on training materials. But the high loss on the test data. Okay, as for the more detailed mathematical principles, why a more flexible model will be more likely to be overfitting. The mathematics behind will be discussed on the week after next week. Teacher Pei Yuan Wu will explain to everyone in more detail. Let's talk about its concept today. Okay, how can I solve the overfitting problem just now? There are 2 possible directions. The first direction. Maybe this direction is often the most effective one. That is to increase your training data. So suppose you want to make an application. You find that there is an overfitting problem. I think that the easiest way to solve overfitting is to increase your training data. So if the training data, the blue dots become more. Although your model may be very flexible, you have a lot of points. So it can be limited. It will still look like the shape of the quadratic curve behind these data. But in your homework, you can't use this trick. Because we don't want everyone to waste time collecting information and so on. This is not the core part of machine learning techniques. We hope everyone will focus more on the core techniques of machine learning, instead of spending too much effort collecting information on the internet and figuring out how to do the homework. This is not what we want everyone to do. You can't collect data by yourself in homework. What can you do? You can do data augmentation. This method is not considered as using additional data. What does data augmentation mean? Data augmentation is you use some of your understanding of this problem. Create new data by yourself. For example, when doing image recognition, a very common trick is, suppose there is a picture in your training data. Flip it left and right. Or crop one part of it and enlarge it, etc. If you flip left and right, your data will double. This is data augmentation. But you should pay attention that data augmentation can't be done casually. This data augmentation, the augmentation should make sense. For example, in image recognition, you rarely see people turning the image upside down as augmentation. Why? Because these pictures are all reasonable. Flipping a photo left and right does not affect what is inside. But it's weird if you turn it upside down. This may not be training material. It may not be the image that will appear in the real world. If you show the machine these strange images, it might learn weird things. So data augmentation should base on the characteristics of your data and the understanding of the problem you are dealing with to choose the right way of data augmentation. Okay, here is the part for adding information. What other solutions do we have? Another solution is to limit the flexibility of your model and give it some restrictions. For example, suppose we restrict our model to a quadratic curve. That is, we somehow know that the relation between x and y has the form of a quadratic curve. It's just that we don't know the coefficients that are associated with the quadratic curve. You might wonder how we reached this conclusion. How should one know how constrained the model needs to be? This depends on your understanding of the problem. Since you designed the model, how constrained or flexible should the model be to get a good result is something only you can answer. Different models and different designs would lead to different results. Now, assume that we already know that the model is a quadratic curve. This piece of information will greatly restrict our options when choosing a function. Since the quadratic curve is very simple, there aren't too many variations, and it generally looks something like this. So, when the training data is limited, there aren't too many functions for us to pick from. For example, when only 3 points are given, we might just pick a function that is close to the real distribution, because the functions we can choose from are quite limited. This is the second method that we can use to achieve better results and solve the problem of overfitting by giving your model some restrictions. There is a chance that your model would closely resemble the real data distribution. Then, you might have a chance to get good results. Is there any other way to further limit the model and create more restrictions? For example, we can give it fewer parameters. If we're dealing with deep learning, we can decrease the number of neurons, perhaps changing from 1,000 neurons per layer to only 100 neurons per layer. Or, you can make models share parameters by forcing some parameters to have the same value. If you didn't quite understand this part, do not worry. We will come back to this part in the future when we discuss CNNs. This is just a small preview of it. When we talked about the network architecture earlier, we mentioned the fully connected network. The fully connected network actually has a more flexible architecture, whereas a CNN has a more restricted architecture. You might think that CNNs are better. After all, most tasks regarding computer vision are done by CNNs. Is a CNN, a superior model, really less flexible? Indeed, it is a relatively inflexible model. What's great about it is that the flexibility of the model is restricted with the characteristics of images in mind. The set of functions found by fully connected networks is larger in size when compared to the set of functions found by the CNN model. The set it forms is actually a subset in the set of functions found by fully connected networks. However, it is the restrictions given to the CNN model that makes it perform better than the fully connected network. We will learn more about CNNs in the future. Are there any other methods? One way is to use fewer features. The teaching assistant has already demonstrated this method. Originally, we were using 3 days of data. When we choose to only use 2 days of data, the result actually got better. This is one of the techniques. There is another technique called early stopping. Early stopping, regularization, and dropout are all things that will be covered in later courses. These 3 techniques were included in Homework 1. Early stopping is actually already implemented by the teaching assistant in the sample code. So it's fine if you don't know what it is. Just execute the sample code. And that's it. Regularization is left out and it's up to you to implement it. If you don't know what regularization is, that's okay. The sample code should be enough for the simple baseline. If you want to improve your work, you can do some research on regularization and implement it by yourself. As for dropout, it is another common way to restrict models when we're working on deep learning. We will elaborate on this later. Too many restrictions could also impact the performance. Why can't we restrict the model too much? Suppose now we put more constraints on the model, and we force our model to be a linear model. It must be written as y equals a plus bx. Then the functions which can be produced by your model must be straight lines. Given these 3 points, there is no straight line which can pass all these 3 points. However, you can find a straight line which is relatively close to these points, but you can't find any straight line which can pass all these 3 points at the same time. In this situation, your model is too restrictive. You won't get good results on the testing data. But is this overfitting? This is not overfitting, because you are back to the problem of model bias. So under this situation, the result on the slide being not good is not because of overfitting, but because you put too many constraints on your model. The constraints are too many, so you have a problem of model bias. So you will find that there is a contradiction here. A contradiction occurs here. Today you make your model more complex, or make your model more flexible. But what is the complexity of a model? What is flexibility of a model? In today's class, we didn't give a clear definition, but only a concept. But in the class of the week after next, you will be really clear on what it means that a model is complex, and what it means that a model is flexible. How to measure the complexity of a model. How complex is it? Let's first explain it intuitively. If we say a model is more complex, it means that it can produce more functions, and it has more parameters. This is a more complex model. Then suppose we have a more complex model. If you look at its training loss, you will find that when the model becomes more and more complex, the training loss can get lower and lower. However, while testing, when the model becomes more and more complex, at the beginning, the test loss will decrease. But when the degree of complexity is higher than a certain level, testing loss will suddenly increase. The reason is that when your model becomes more and more complex, and its complexity exceeds a certain degree, the overfitting happens. So on the training loss, you can get a better result. Then on the testing loss, you will get a higher loss. Of course we expect that we can choose a proper model, not too complex and not too simple. On the training data, it can give us the best result, give us the lowest loss, give us the lowest testing loss. How to find such a model? A very intuitive method that you are very likely to do. If no one tells you what to do, you might do this intuitively. The method is the following. After we upload a submission to Kaggle, we can get the result immediately. So suppose we have 3 models, and their complexity is not the same. I don't know which model has proper complexity. To get the best result on the testing data, overfitting will happen if you choose a too complex model. But choosing a too simple model causes the problem of model bias. How to choose a proper one? What to do if we don't know? Get the results of these 3 models. Upload them to Kaggle, and you can know the scores immediately. After checking which score is the lowest, the corresponding model is obviously the best model. But it is not recommended for you. Why is not recommended for you to do this? Let's take an extreme case. We use again the previous extreme case. Suppose there is a group of models, and these models are very useless. The functions generated by the models are useless functions. How big is the number? I don't know, so let's assume that it is 1 trillion. We have 1 trillion models. Without knowing why, these 1 trillion models only learn useless functions. What they do is memorizing the data in the training set. For those data that are not in the training set, they just output random results. Okay, you now have 1 trillion models. Then you upload all the results of these 1 trillion models to Kaggle and get 1 trillion scores. Then after checking all these 1 trillion results to find the best one, you may think that the corresponding model is the best. Because every model is not trained on the test data, and they haven't seen the test data, the results they output are all random. Although on the test data, the results are all random. If you keep trying, you will still find a good result, right? So maybe for model 56789, the function it finds happens to match the test data. So it gives you a good result. Then you will be very happy to think that model 56789 is a good model. This good model gets a good function. Although it's actually random. This good function gives us good results on testing data. So you think that the result is good. I choose this model, this function, as the result of the last upload, as my final result, on the private testing set. But if you do that, you often get very bad results. Because this model is random. It happens to get a good result on the public testing set. A good result is on the public testing set. But when it is on the private testing set, it may still be random. So suppose you are choosing a model today. You all use the testing set we provide. The testing set is divided into a public set and a private set. When you look at the score, you only see the public score. The private score won't be released until the deadline. But suppose you are picking a model totally by the score on the public testing set. That is, using the score on the leaderboard to choose your model. You might be like this. You are in the top 10 on the public leaderboard. But once the deadline is over, you just collapsed like this. You fall out of 300 places. And there are so many people taking courses here. Maybe you will fall out of 1,000 places. Maybe. Okay, this is not folklore. It's no exaggeration. It happens every year. Because this year we will consider the public scores. It means that when we calculate the score, your good results on public will still give you a little point. We don't just consider private scores. We look at both public and private scores. Some semesters in the past, when only considering private scores, your mentality will collapse. If this happens, you will be very, very depressed. Okay, then some classmates will say that. Why do we want to divide the testing set into public and private? Why can't we just divide everything into public? Why am I embarrassing everyone? Why I make everyone worried about the result on the private testing set? Think about it for yourself. Assuming all data is public. I just said that. Even if it's a worthless model, a useless function, it may also get good results on public data. If we only have public testing set today, with no private testing set, then you just go back and write a program that keeps generating output randomly, and then keep uploading the random output to Kaggle, and see when you can randomly produce a good result. Then this homework is over. This is obviously meaningless. It's obviously not what we want. And today, there is another interesting thing here. You know that public testing data is open to the public. You can know the result of the public testing data. Then even if you have a very useless model that produces a very useless function, it may also get very good results. This should explain why in the field of machine learning, on those benchmark corpora, machines can often get unusually good results, which often surpass humans. The so-called benchmark corpora means some data sets are public. For example, Libre speech is a public data set that is used to train speech recognition. Then if you want to test whether your own voice recognition model is good or not, then you train it on Libre speech. Libre speech also has a testing set. Everyone shares the same testing set. Then we can compare the quality of different models. But the problem is that the result of these testing sets is all public. So even if it's a very useless model, that can only produce very useless functions. As long as you train it enough times, you can still get a good result on the public testing set. This explains why, on these benchmark corpora, machines can eventually get results that surpass humans. The most famous example is this. In 2016, Microsoft and IBM claimed at the same time that their models had outperformed humans on speech recognition. Compared to professional transcribers, these ASR models achieved even better error rates. Where are these results from? These are actually done on some benchmark corpora. Here the corpus is named the switchboard benchmark corpus. Do you believe That machines are truly smarter than humans. Just because they perform better on some benchmarks? I don't think so. You don't have to be an ASR researcher. Since you may have seen some related applications. Speech recognition systems are ubiquitous today. Every smartphone has one in it. From your everyday experience, you won't believe that machines have surpassed humans. On real-world ASR, those benchmark corpora are just like the testing set here, namely the public testing set. However, when an ASR system is put into production, the input from the end users will be like the private testing set. The systems may beat humans on the public testing set, which doesn't mean they are still better on the private testing sets, even if the machines are claimed to achieve higher accuracies than the humans. That may not be the case for their accuracies in real-world applications. You know, those claims regarding machines' excellent performance on benchmark corpora are just rhetorics used to hoax the muggles. But in my opinion, it's still responsible of the companies to publish their valid results on the benchmarks. But I've heard worse. A startup from out of nowhere got a government project, which is about ASR, on their dataset. They set a KPI target that their model has to achieve more than 90% accuracy. Yet sadly, they failed. Their performance can't reach 90%, whatever they tried. How could they deal with the project acceptance review? When questioned by the officer, they came up with an excuse that this is due to the poor quality of the given dataset. The dataset has too much noise, they said. So we decided to remove all the noisy data. And now we are able to reach 90% accuracy. They achieved the KPI target with their cleverness. In fact, this isn't the most terrible of them. More precisely some strange startups, will show you their apps and say, "Hey, this is our ASR system. Did you know? Its recognition results are as good as those from the Google ASR API." How did they do that? They called the Google API stealthily in their app. So there are all sorts of weird things happening. You can just ignore all those flattering comments on those doubtful APIs. The reason I've mentioned all these is that I'd like to tell you why you should split the testing set into the public and private parts. Actually, you must not tune your model on the public one, because you may still get poor scores on the private one. But in this class, your performance on the public set are included in your final score. This would be a problem. Some people may exploit this and sacrifice their private set scores for better performance on the public set by constantly generating random predictions. Those random predictions are then submitted to Kaggle to see if they can score higher on the public set. In order to prevent you from doing this, there is a daily submission limit. You are thus discouraged from getting good results with a poorly trained model, simply by trial and error. Which way of model selection would be more reasonable? As implemented in the sample codes by the TAs, our method of choosing the best model for inference is as the following. You have to split the training data into two parts. One is called the training set, and the other is called the validation set. As we saw in the previous sample code, 90% of the data makes up the training set, and the other 10% will be used as the validation set. You can train a model on the training set and test its performance on the validation set. Based on the scores on the validation set, you can pick the model with the best performance and submit its prediction to Kaggle. Then the public set score may be a better estimate of the model's ability. That's because the models are chosen according to their performance on the validation set. So your public testing score somehow reflects your private testing score. You are less prone to the situation that you did well on the public set, but failed on the private set. At the same time, when you saw your public set's results, you can't help but try to modify your model. If you have a bunch of models doing well on validation sets, but failed on the public sets on Kaggle, it is very hard for you to simply ignore it and be confident in your model. But if you adjusted your model too many times, trying to fit the public testing set, you are possibly overfitting to the public testing set. If that's the case, you will receive poor results on the private testing set. Fortunately, we have set a restriction on how many times you can upload your model. So you won't be able to fit the public testing set excessively anyway. We are trying to prevent you from overfitting the public testing set. Okay. Since the results of public testing set are available for everyone to see, and you can be named yourself whatever you like. If some person gets the first place, he might be very proud and change his name to something like, "I got the first place in the first try," or "I'm just an auditor," while he is actually not. If he changed his name to, "I'm actually just an auditor, but got first place easily," you might be very nervous. Especially if you know him. If one of your close friends won the first place, you will be nervous. Then you might say, "Don't be proud. I'll beat you soon." But actually, you don't need to waste your time trying to beat him. Based on my experience, those who score very good on public leaderboards are likely to fail on private sets. So don't celebrate too early if you get good results on public sets. The best way to determine the quality of a model is to use validation loss. Just pick the one with the lowest validation loss. Don't care about the result of public sets too much. That being said, I know that it is hard for you to ignore the public leaderboard because you saw the score. So the public leaderboard may slightly affect your confidence in your models. But I suggest you to not care too much about the leaderboard. Did I answer your question clearly? Okay. If there are any other questions, I will answer those later. Oh, I forgot to repeat that student's question. For those who watch our videos online, let me repeat the question. His question is, are you saying that we shouldn't rely too heavily on the result of the public testing set? Ideally, yes. You should use only the validation set to choose between your models. Then simply upload the best one. If you manage to pass the strong baseline, don't change it anymore. This is how you avoid being overfitting to the testing set. Okay, but there is still a problem here. How should we divide the training set and validation set? If in TA's source code, the sets are randomly divided. But you might think that the dividing is bad. Maybe I picked out a very strange validation set, which resulted in poor scores. If you are worried of this issue, maybe you can use n-fold cross-validation. How does n-fold cross-validation work? You separate your training data into n equal parts. In this example we set n equal to 3. After that, take one of them as the validation set. The other two will be your training sets. Then, you have to repeat this 3 times. So what you do is, first use the first and the second copies to train the model, and the third copy as the validation set. Then choose the first and the third copies as the training sets, and the second copy as the validation set. Lastly, pick the first copy as the validation set, while the second and the third copies are the training sets. So you end up with 3 models. But you don't know which one is the best. Now, use all 3 models to run through all 3 data sets. That is, the training and the validation sets. Do this for all 3 models. And record the performances on the 3 sets. For every model respectively. Take the average performance on 3 data sets for every model, and see which model has the best average result. Let's assume that model 1 has the best result. The result you get with these 3 folds is that the model 1 performs best. Then you use all the data in the training set to train model 1. Then use the trained model on the testing set. Okay, this is n-fold cross-validation. This is the guide for the early stage of this course. It can take you to win all the early instance dungeons. Then the next question you might want to ask is, The number of viewers last Friday. February 26th. We talk about at the end of last week. How did it turn out? Okay, this is the result. Most people chose the 3-layer network last week. So we put the 3-layer network to test. The following is the result of the test. We did not further adjust the parameters. After we make our choice, we don't change our decision. Just use it directly. Okay, the result is here. The horizontal axis on this graph is from January 1, 2021, and going on. The red line is the ground true. The blue line is the predicted result. February 26th is over here, which has the highest viewers count. In 2021. What about the machine's prediction? Wow, it's very miserable, the gap is very big. The gap is 2.58K. Thank you everyone for making this model inaccurate. By spending a lot of effort last Friday. Clicking on this video. So this day is the most watched day this year. Then you might start to wonder that. How the other models perform. Actually, I also ran the single layer, the 2-layer, and the 4-layer model. All models perform miserably. The error of the 2-layer and the 3-layer are both over 2K. Actually, the 4-layer performs better than the single layer, which has an error of about 1.8K. These 4 models predict a low point on February 26 coincidentally. However, February 26 is a high point. However, we can't blame that. The model predicts a low point because based on previous data. There is no one who will learn machine learning on Friday. Everyone has fun on Friday night, right? The number of viewers on Friday usually is the least. But there has an abnormal situation on February 26. Okay, you can't blame the model for this. The situation should be considered as another form of error. This form of error, we called it a mismatch. Then some people claim that mismatch is also a kind of overfitting. This is okay too. It's just a matter of definition. What I want to express here is that the reason for the mismatch is actually different from overfitting. In general, you can overcome overfitting by collecting more data. However, mismatch implies that the training data and testing data have a different distribution. When training data and testing data have a different distribution, it doesn't help, even if you increase the amount of training data. Actually, in most homework in this course, we will not encounter this kind of mismatch problem. We have designed the problem carefully. So the distribution of the data is similar to the testing data. Take homework 1, predicting COVID-19. As an example. Suppose when we divide training data and testing data, we set the data in 2020 as training data, and the data in 2021 as testing data. The mismatch problem may be very serious. We have actually tried this setting. If you use 2020 as your training data and 2021 as testing data, whatever you do, the performance is miserable. Training on any model is miserable. Because the data distribution in 2020 and 2021 is actually different. If you use the 2020 data to train and test on the data in 2021, you will have an incorrect prediction. The teaching assistant used other methods to split training data and testing data. Most of our homework will not have a mismatch problem. Except for homework 11, because homework 11 is designed for the mismatch problem. Assignment 11 is also an image classification problem. This is its training data. Looks pretty normal. But its testing data looks like this. So you know that under this circumstance, there is no use in adding data. Adding data cannot make your model perform better. So how to solve this kind of problem? I'll talk about it at homework 11. Okay, then you might ask that. Why I know the cause is a mismatch. In my opinion, the judgment of mismatch depends on your understanding of the data. You may need to have some understanding of how the training data and testing data are produced. Then you can decide that whether the mismatch problem is encountered. Okay, this is the guide for our homework.